next, I'm going to be talking about a new distribution. You may ask the question, why do we need a new distribution? Because we are going to be talking about a new statistic and a new hypothesis test, a new comparison that we would like to do. That new comparison is going to be the equality, or whether the ratio of two populations is equal to a constant value or not, kind of hypothesis test. So now we are going to be interested in a sigma 1 square from population 1 and sigma 2 square from population 2. We are going to be interested in the ratio of those two as a null hypothesis. Actually, if you take this to be equal to 1, we mean that we are talking about equality of variance values. And we are going to try to test this hypothesis, of course, using the sample variance values. So now when it comes to this comparison of the, or putting sample variance values in an equation such that we are going to obtain a hypothesis test for comparing population variances, we are going to be sailing in new waters, I may say. So, and that new random variable, that new distribution will be denoted with F, which actually is the first letter of Fisher, and that's Fisher's F test, or F random variable. So an F random variable is defined to be the ratio of two independent chi-square random variables, each divided by its degrees of freedom. So basically, we are going to have a distribution and another independent distribution. We are going to have two independent samples from those distributions, and that from that independent sample, we are going to be obtaining a chi-square random variable. And from this one, we are going to be obtaining another chi-square random variable. You may call this 1 and 2 if you like. Here, they are denoted with W and Y. So this is actually W and Y here. And we are going to, and remember what this chi-square random variable is. It is the degrees of freedom, sample variance divided by population variance, is actually a chi-square random variable. And actually we are going to divide these by their corresponding degrees of freedom. And here for the numerator, this is going to be U. So therefore we are talking about the degrees of freedom of this sample here. And we are going to be dividing here by mu, the lowercase mu in Greek letters, to denote the degrees of freedom of this random variable. So once we do that, we are going to be obtaining a new random variable, F, which is a new distribution. F distribution, the shape will look like a chi-square distribution. Let's just talk over about this one. Note that since they are both chi-square random variables, and chi-square random variables are non-negative values actually, the ratio here is, it cannot be a negative value, right? So if you have 0 here in the numerator, then this is going to be a 0 here. If you have 0 in the denominator, then this is going to go to infinity. So this is going to be a 0 to infinity. The domain of F is going to be from 0 to infinity. And the distribution, this kind of looks like a chi-square distribution. But there is one thing here. Unlike chi-square distribution with a single degrees of freedom, we are going to have two degrees of freedom parameters. One U, which is the numerator degrees of freedom, and mu, which is going to be the denominator degrees of freedom. So, well, depending on U and V, the mu values, we are going to have different F distribution shapes. And this, the very same thing that we have discussed before, like the type 1 error here, significance level will still be applicable. So the significance level or type 1 error will be denoted by this region here, this area here, right? And this corresponding point, which has this tail probability, is going to be denoted by F at a certain alpha value, significance value at U and mu degrees of freedom. And this can be read from your textbook in the appendix, actually. So, okay, this is one of those F distribution tables. Note that this is going to be, since F distribution has 2 degrees of freedom, 1 in the numerator, then 1 in the denominator, the T distribution tables will be a little bit more complicated. Or actually, it needs to have it takes more pages, let me say, to give a more true covering of F distribution values. For instance, when numerator is equal to 5 degrees of freedom and 8 degrees of freedom, you can find that the corresponding F value is equal to 3.69. On the other hand, note that this is going to be applicable for when alpha is equal to 0.05. So here, this table only belongs to the significance level of 0.05. Compare it with t-distribution table or normal distribution table, where you have all different alpha values. So given a single alpha value, we are going to have this, since actually each of these values here will correspond to a different F distribution. So the single alpha 0.05 is a single alpha value 0.05 will correspond to, if you have 5 to 8 degrees of freedom, to that value. Now, one very important thing here, these alpha values, unfortunately, in textbooks actually only are covered from, usually from alpha is equal to 0.25 or maybe 20, 0.10, 0.05, and 0.01, which means we are only interested in the right-hand side. What about the left-hand side? We may be interested in the left-hand side because we are talking about the ratio of two variances, right? So this ratio might be greater than 1, so it may be a large value, but it may be very much smaller than 1. We may be talking about these low values. Hopefully there is a very nice relation in F distribution. So if we are interested in the left-hand side area, which is called lower tail quantile, and this is denoted by F subscript 1 minus alpha U and V degrees of freedom. So at U and V degrees of freedom, we are interested in the case that this area is equal to 1 minus alpha, find this corresponding value. What is this value equal to? And this table does not exist in your textbook, but you can use this relation. So how are we going to use this relation? Since the quantity that we would like to find is equal to this, in your textbook, what you do is you search for the F value with the corresponding alpha value. Alpha value is going to be small value like 0.05, 0.01 with mu and U degrees of freedom. So you just reverse the order of those two, and with the given alpha value, you can, by this way, determine the corresponding left-hand side probability or lower tail quantile. So how are we going to conduct the test? As I said, we are going to be interested in ratio of ratio of variance values, and here the equality is given. So actually it means that this is actually equal to 1 is the kind of question that we are interested in. So if this is the question that we are interested, or this is the hypothesis that we are interested in, here this is how we are going to conduct the test statistic. So if 0 is equal to a chi-square random variable from the first sample and the second chi-square random variable from the second sample, each divided by their corresponding degrees of freedom. Replacing these chi-square random variables by n1 minus 1 sample variance of the first sample divided by population variance of the first population, and this is going to be divided by n1 minus 1. Note that these will cancel, and you do the same thing for the denominator, you obtain the same result. Therefore, we are going to be obtaining this value here. So this F0 variable will be F distributed with this U, and or let's call it N1 and N2 minus 1, of course, degrees of freedom. Now, if this is the hypothesis at hand, and note that how we apply the hypothesis, that we always take that the null hypothesis true, and based on this condition, we prepare our test statistic, then compare it with the tabulated values. So what we do here is, when you assume that these two are equal to each other, these sigma values are going to be canceled. So our F0 value is going to be equal to S1 square over S2 square. And we are going to be comparing this F0 value to depending on the alternative hypothesis. What do I mean by that? If, for instance, the alternative hypothesis variances are not equal to each other, we are going to be comparing this F0 value here with the upper critical value, which is alpha over 2 and 1 minus 1 and 2 minus 1 alpha over 2 corresponding to the right-hand side, right tail here. So I'm talking about this part here. And when it comes to the left-hand side, note that since it's a two-sided test, we should check both of these conditions. And again, note that the F distribution is not a symmetric distribution. So this is going to be already positive. So taking absolute value and comparing with only one side would not work. So we also compare it with the left-hand side. The left-hand side is going to be 1 minus alpha over 2. So it's going to be this lower, the left-hand side lower quantile here. It's going to be n1 minus 2 and 2 minus 2. Note that these degrees of freedom will still be the same. But when it comes to reading this value from the table, what you are going to do is this is going to be equal to 1 over f alpha over 2 and 2 minus 1 and 1 minus 1. It is due to this relation. I just point here. So if the alternative hypothesis on the other hand is such that sigma 1 square is greater than sigma 2 square, we are going to be interested only one side here. So therefore this upper critical value is going to be equal to F distribution at a significance level of alpha and the corresponding degrees of freedom. So, and the p value is going to be actually the F0 value greater than the determined F0 value. So any F distribution value greater than the computed one. And the very same thing when sigma 1 square is less than sigma 2 square. This time we are going to be interested in the F distribution value for the lower alpha 1 quartile, which is 1 minus alpha 1. Therefore, to find this, again, to read this quantity from this table, we use the formulation here shown to you. Now, there is an interesting thing which I would like to mention. These derivations are determined using this null hypothesis. But be careful where we use this null hypothesis. We have not used this null hypothesis here up to this point. So this point, test statistic here, it says, within those frames is irrespective of the type of the null hypothesis. What I mean is this: if the null hypothesis were like that, you can put it also in this form. So variance of the first population is 2 times the variance of the second population, if it's of this form, or it could have been written like this. So if the null hypothesis were given in this fashion, you still could have used F distribution and this test. How? Up to this point, it is still the same. Here, note that instead of this relation, we would be using this relation. So the F0 value would have been equal to S1 square over sigma 1 square, or let's write instead of sigma 1 square, 2 sigma 2 square over S2 square over sigma square. So these will cancel. So F0 value would be equal to S1 to S2 square. So you would calculate these values from your samples and divide by 2, and you would find the corresponding F0 value and do the calculations or the comparisons here. So be careful about that. Okay, and the confidence, when it comes to confidence interval, we follow this very same strategy. The F value is defined by this way, but actually there's an important trick here I would like to mention, and it's totally based on very simple arithmetics. There's no fancy here in terms of statistics. Now we are going to define F here in this form: the second sample variance divided by the second population variance, and here terms related with the first population and sample. When you write it like that, we can use these left and right hand side limits. Again, please be careful. Here is going to say n2 minus 1, n1 minus 1, n2 minus 1, and 1 minus 1. And here, this is going to be this F distributed random variable. This is going to have the numerator as n2 minus 1 and the denominator as n1 minus 1 degrees of freedom. So when you put here instead of this F and rearrange, you are going to be obtaining this result. This is also in your textbook. be careful with the upper and lower critical values, the F values related with those upper and lower critical values. Here it says n2 minus 1 and 1 minus 1. For those who may think that why did we put here the inverse of the first definition of F, where we use S1 square over sigma 1 square. Actually, it doesn't matter which one you use, but is there a specific reason? Yes, because when we divide those, since we would like sigma 1 square over sigma 2 square term here in the middle, then when we put it in this form, sigma 1 square is going to be in the numerator, whereas sigma 2 square is going to be in the denominator. And the sample various terms will be on the left-hand side and the right-hand side, since they are computed from the samples. This is the only reason. And when you do that correctly, you end up with these degrees of freedom. So please be careful about this. Is n2 minus 1. However, here in the numerator, we have sigma square. So please be careful about the order of these. Okay, now comes a question. We have two production streams, and they are known to be independent. So we have one stream here, which actually denotes a kind of a factory, but actually it produces these, I don't know, products, and another stream which manufactures these again products. And we are interested in the concentration of some material in each of these products. Right? And what we are interested in comparing is the variability of this and these two streams. That's because of quality concerns maybe. So, and what we would like to compare is there suggested variances of concentrations two tanks are different at 0.10 significance levels. So our hypothesis, if this is stream 1 concentrations in, let's define it properly, in stream 1, and x2 are actually concentration, singular, concentration of a product in stream 2. Actually, if you'd like to write it longer, concentration of a substance in a product in stream 2, but I think you got the idea. So what we are interested in is, we would like to, as a null hypothesis, we would like to check whether these two are equal to each other, variances, or as the alternative hypothesis, they are not equal to each other. This is exactly what is asked. Of course, you can also show it that way. Let's call it 1 is equal to this one, and 2 is, I'm sorry, 1 is not equal to, population variances are different from each other. So this is the hypothesis test at hand, and we would like to conduct it at a significance level of 0.10. So what we do is we collect two samples, and this consists of a sample of 10 observations, and the second one is a sample of 16 observations. And what we obtain here is actually, if we go back to the equations related to this, okay, let's see, let's get rid of these. Here actually this is an equality of hypothesis as the null hypothesis. So therefore we are going to be using the ratio of sample variances. So from the samples, what we would like to, we have to compute are the variances. And they are already found, but please be careful. It says sample standard deviations. So these are sample standard deviations, not variances. So we have to F is here is going to be equal to 1.96 square divided by 2.13 square. And when we do that, do the operation, the result is 0.85. So we are going to check this F0 value, whether this is between some certain limits or not. This is the question at hand. If there are certain limits that we are going to find, then null hypothesis would not be rejected. Otherwise, we would reject the null hypothesis and say that variances are not equal to each other. So what are the limits that we should consider? Here, since this is a two-sided test, we would be interested as alpha over 2 and n1 minus 1 and 2 minus 1 value. And alpha over 2 is F 0.05, and n1 minus 1 here is going to be equal to 9, and n2 minus 1 is going to be equal to 15. So using your textbook, you come up with F0 0.9 and 15 degrees of freedom. This is going to be equal to 2.59. let me write this value also clearly here again. This is equal to F 0.05 with 9 and 15 degrees of freedom. As you can see, this F0 value is smaller than that value. That's great. Okay, now we also have to find the left-hand side. The left-hand side value is going to be equal to 1 minus alpha over 2, and again, and 1 minus 1 and 2 minus 1, which is going to be actually equal to F 0.95 with 9 and 15 degrees of freedom. Now, here's the point. In your textbook or in any textbook, you are not going to be able to find F distribution values related with the left-hand side probability of alpha over 2 or an alpha or a significance level of 0.95. What you should do is use this rule I have shown you previously. Where is that? This one. So let's use it. It's going to be very simple. So this is going to be, if I can find my cursor, yes. So this is going to be equal to 1 over F 0.05. You just replace those degrees of freedom. So this value can be found from your textbook to be equal to 3.01. Therefore, 1 over 3.01 is going to be 333. Now, therefore, we have two sides here. Since this is 95 with 9 and 15 degrees of freedom, this is equal to 0.332. Note that this, our F0 value that we have found, lies between those two. Since this is the case, we should say that, this time I'm not going to write here, it's already too much messy. There is not substantial evidence or significant evidence to suggest that variances differ. So actually we cannot reject that the variances of two streams are equal to each other. Now, as a second part of the question, I can show how to solve this question using confidence intervals. And for that, I'm going to directly use this formulation here, this one. So here, let me solve the question here. Probability of S1 square, S2 square. Actually, that ratio was already found. That was my F0 value here and F0 value here. I already found it to be equal to 0.85. What I need is F 9.95. So this is going to be the corresponding degrees of freedom, but this time this is going to be the second sample. So it's going to be 15 and 9. Smaller equals sigma 1 square over sigma 2 square divided by, again, 0.85 F 0.05 with the corresponding 15 and 9 degrees of freedom. The result is going to be equal to 0.90. Okay, so you can directly read this value from the table, and that value is going to be equal to, if I can find it, let's see. This is going to be equal to 3.01, and this value is going to be equal to 1 over F 0.01 with 9 and 15 degrees of freedom, which I have already shown in the first part of the question is going to be equal to 1.59. So therefore, when you solve this question, the result is going to be equal to probability that my ratio of variances is between those two values, and those two values being, it's going to be 2.56 is equal to 0.9. Therefore, at a significance level of 90%, my ratio of sigma variance of the first process to the second process is going to be between 0.328 and 2.56. Here is the important point here. Since the ratio here 1, since 1 lies here in this interval, we won't be rejecting the null hypothesis. You may ask why 1? In the previous questions, we checked for whether 0 was included in the interval or not, because in the previous cases, we were checking things like mu1 minus mu2 is equal to 0. And we found a confidence interval for mu1 minus mu2. Therefore, we check whether this is equal to 0 or not. For this case, we are interested in the ratio. And if the ratio now includes 1, That means we cannot reject the possibility of the equality of two variances. This is the issue. Okay, now comes the last topic. I guess you can very easily see we follow the very same procedure we follow for the last two chapters. Now we are going to be talking about population proportions, and we have again we are interested in two Bernoulli distributed random variables, but we are not interested in their probabilities, but we are interested whether the probabilities are equal to each other or whether they are not equal to each other or not. Of course, one-sided case also possible, but I'm going to be talking about solely on two-sided case. The other cases pretty much straightforward. So what we are going to do is the very same procedure. If again n1 and n2 are high enough, then we can apply normal approximation. The test statistics is going to be equal to the difference between their point estimates and their expected values, P1 minus P2, divided by their corresponding, these are the variances of P1. This is variance of P1 hat, and this is variance of P2 hat. Actually, you can go back to the previous lecture and see that these are already found. So we are going to add these and take the square root to find the standard error of this estimator, I may say. So when we use this null hypothesis, again, we use now at this point, we use a specific form of null hypothesis. In this case, P1 minus P2 is going to be equal to 0. So we get rid of this part, right? And now here we use P1 minus P2 hat values. Note that here also we use a single P value. So this is going to be basically equal to, because we assume that P1 and P2 are equal to each other. Therefore, this is going to be P1 minus P over N1 plus P1 minus P over N2. Therefore, when you take into the common parenthesis of P times 1 over 1 minus P, is going to be N1 plus N2. And they are going to be all in square root. As you can see, you obtain this result. So instead of P1 here, we are going to be using its maximum likelihood estimator. Instead of P2 hat, we are going to be using its maximum likelihood estimator. Now in the denominator, we have terms related with P, which we do not know. Therefore, we also replace this by this estimator. So assuming that actually they come from their P values are constant, you can use this estimator. So you sum all the sample values, sample sizes, and the corresponding positive answers here, or the number of successes here and here. So this is going to be the total number of successes in both samples divided by the total sample size consisting of two samples. This is going to be an estimate of the common equal p-value. Note that at this point we have used this assumption, this assumption about the null probability, null hypothesis here. And once we do that, we obtain this Z0 value, and this Z0 is going to be again standard normal distributed, right? If the null hypothesis holds, like the other cases. Okay, so let's test this, or let's employ this technique on an example. A new drug is tested, and again, the formal procedure is we are going to have a control group of placebo and a test group with new drug. And here, let's say that at the beginning, we have 200 patients, and randomly, we select 100 here and 100 here. So here, and 100 patients here and 100 patients here. Okay, when we apply this new drug, and these guys with the placebo, we tell them that they are using the drug, 19 of them got better out of 100. And in the test group, 27 of them got better. Does the new drug affect the patient's condition? This is the question at hand. And now I again use effectiveness as both a positive or negative effect. So in this case, the hypothesis test would be equal to, actually before even taking these samples, actually let me write the meaning of P and P1 and P2 here. P1 is the probability that that a patient who is told to have taken a treatment but no treatment is given gets better. Well, that's a very long definition, but I think that's pretty much captures the spirit. And P2 is the very same thing, but actually given the treatment. So we would like to test whether P1 is equal to P2 versus P1 is not equal to P2 at a certain significance level, and let that level be equal to 0.05. I think that's what is asked also in the question, at least in my notes. 0.05 is the probability here. So in order to solve this question, we are going to be just using this equation. This equation says just use the point estimates here, and for the standard error, use this ChE. So P1 hat is going to be equal to 19 over 100, which is 0.19. P2 hat is going to be equal to 0.27. So our Z0 value is going to be equal to 0.19 minus 0.27 divided by, in square root, let me go back, we have P1 minus P. So we need a common P value, and this is how it's found. It's going to be total number of successes. Is going to be successes from both groups divided by the total size. So this is going to be equal to 46 over 200, which is going to be equal to 0.23, I guess. So here we are going to have 0.23 multiplied by 1 minus 0.23. And make it larger. And multiplied by 1 over 100 plus 1 over 100, if I've done everything correctly. And when you calculate this, the result is going to be equal to 1.34. So what we need is to compare it with some critical value. So the upper critical value here, since alpha is equal to 0.05, we are going to interest 0.025, which is equal to 1.96. And comparing these two, as you can easily see, Z0 value, which is equal to 1.34, is smaller than Z0.025, which is equal to 1.96. Therefore, there is insufficient evidence to suggest that the new drug is effective. So that's, again, from a bird's eye point of view. If you look from the question, actually 27 people got better compared to 19 people got better using placebo. On the other hand, still, this is actually, we cannot assign this difference to our real effect, but only due to inherent variability, the noise, background noise of the process, I may say. And when it comes to confidence interval approach, actually we are going to be using, I haven't written the formulation for confidence interval approach, but it's going to be the same thing. So we have a lower limit, and the Z value here is going to be, again, 0.19, this difference. So 0.19 minus 0.27 minus P1 minus P2 divided by this whole number, which is, I'm going to just write the value here, 9.5. So this value is actually equal to this value here. Anyway, this is between those two limits, right? And this is equal to 0.95. And when you do the maths here, I would like to, all right, the result is going to be equal to minus 0.37, smaller than P1 minus P2, smaller than 0.97 with a 0.95 probability. So note that since P1 minus P2, since this includes 0 here, therefore, it is possible that P1 minus P2 is equal to 0, which is suggested by the null hypothesis.